Section 20.5 Charge Transfer Bands. Charge transfer transitions involve significant change in the electric dipole moment of the transition metal complex because of the electron flow from the ligands to the metal or from the metal to the ligands. This kind of transitions are much more intense than the DD transitions. So if you look at the UV-vis spectrum of a transition metal complex, and if you see a huge peak, a huge band, very likely it involves charge transfer. In the next section, you'll learn that the intensity of light absorption is proportional to the change of the electric dipole moment squared, approximately. Charge transfer transition frequencies, or wave numbers, or colors, are strongly affected by the solvents of the transition metal complexes with different permittivity. Permittivity is a material's ability to resist electric field. And why is that? Well, different solvents with different permittivity will have strong impact on the change of the electric dipole moment in the transition metal complex during an electronic transition. There are two different types of charge transfer, from ligand to metal, from metal to ligand. So first, let's look at this LMCT transitions. Electrons flow from the ligands to the transition metal. LMCT transitions may occur when the metal is in a high oxidation state. So this means we have quite a few positive charges on the metal. And this metal is ready to accept electrons from the ligands. And also you may picture this. We have very low energy, empty d orbitals, ready to accept electrons. Meanwhile, the ligands often contain non-bonding electrons. Why is that? Well, non-bonding electrons have higher energy than bonding electrons. So it's easier to give away the non-bonding electrons than the bonding electrons. So essentially, we're just talking about the interaction between the empty d orbitals of the transition metal and the occupied orbitals of the ligands. So when this empty orbitals have very low energy, and when those occupied orbitals on the ligands have very high energy, and then of course electrons flow spontaneously from this high energy occupied orbitals to this low energy unoccupied orbitals. The second type is metal to ligand charge transfer, MLCT. Well, obviously, if the ligand has low energy empty orbitals ready to accept electrons, while the metal has high energy occupied d orbitals that are ready to give away electrons, and then MLCT transition will occur. So again, MLCT transitions may occur when the metal is in a low oxidation state, ideally with an oxidation state of 0. In that case, this metal has d electrons in relatively higher energy orbitals. And then you need ligands that contain low-lying empty orbitals to accept the d electrons from the transition metal. So those low-lying acceptor orbitals in the ligands are often low-lying pi star orbitals. And very often it include this kind of structures. Diimines such as this 2 prime bipyridine, or BPY. So this 2 prime are referring to the position of this link. In 110 phenanthroline are often involved in MLCT, only because this kind of structures have low-lying pi star orbitals ready to accept the d electrons from the transition metal.